Hello, this is the last chapter that we cover in our Chemistry 120 class, an introduction to general chemistry. This chapter will kind of reflect what we've talked about previously in chapters 1 and 2. We're going to focus on the nucleus in the atom. We're looking at the protons and neutrons. We are not looking at the electrons circling the nucleus. So we're going to focus on just the nucleus and the energy emitted by the process called radioactivity. So radioactivity is the process where atoms emit energetic particles or rays, and these emanate from the nucleus of the atom. So a throwback to chapter 1 and 2, we're going to be looking at atomic symbols, and we will call them nuclear symbols because we'll combine the atomic symbol, atomic number, mass number, and relative charges. So we've seen this type of slide before, again in chapter 1 and 2. This is a nuclear symbol where we have the name or the symbol for the element, which we get from the periodic table. We have the mass number. Remember, the mass number has to be a whole number. It's not measured but counted, and it is the number of protons and neutrons in the nucleus. So you either have a proton or you do not, or you have a neutron or you do not. So it's just like counting eggs. There's 12 eggs in a dozen. In this case, there are number of protons and neutrons in this boron atom add up to 11. Below the mass number is the atomic number, and the atomic number is represented on the periodic table, and it is represents the number of protons in the nucleus. And remember, the protons are positively charged. So the protons, there would be 5 positive protons here. And if we were looking at the atom in total, there must be 5 negative electrons orbiting the nucleus in order for the boron atom to be electrically neutral. All right. So boron, the 5 defines boron. The atomic number always defines what the element is. All atoms that have 5 protons in the nucleus in the universe are considered boron atoms. This isotope, let's go back and talk about what isotopes are. Isotopes are atoms of a particular element, such as boron, that have different numbers of neutrons. So an isotope is also referred to as a nuclide, and so there are different nuclides of boron. There's a boron 11, which we see here, and then there's also a boron 10. So one of the questions I would ask here is, what is the difference between boron 11 and boron 10? And again, that's the way we speak this, boron 11. So it's the chemical name followed by the mass number, boron 11, or boron 10. And you should say the difference is boron 11 has 1 more neutron than boron 10. Also here, they both have the same number of electrons. They both behave chemically the same. What is the only difference between these two atoms? Well, it's the neutron, and physically that would show up as a difference in mass. All right, so on this slide we see that there are 3 isotopes of carbon. There is carbon 12, which has 6 protons and 6 neutrons. Carbon 13, which has 6 protons and 7 neutrons. And again, carbon 14, which we've talked about previously in radiocarbon dating, has 6 protons and 8 neutrons. So these are called the isotopes of carbon, or the nuclides of carbon. And all of these would behave chemically the same. All right, some isotopes are stable. They stay intact. Others, the nucleus becomes unstable and they fall apart. And when they fall apart, they release energy, which we call radiation, radiation just means energy from a point source. And that could be heat coming from your body, and your body's the point source, or it could be the filament in a light bulb. That's the point source. So those are all types of radiation. It just means energy coming from a point source. But what we're going to focus on in Chapter 9 is the types of radiation, or the types of radiation that are ionizing, which would be alpha particles, beta particles, and gamma rays. So an alpha particle is symbolized by the symbol helium. And let's see if I can get a pen up here. A helium, so it's alpha, can be written this way. It can be written as helium 4-2, or it can be written as helium 4-2 with the 2 positive. And so that's what we see here in the blue box. And that's what I expect for you to be able to choose any one of these symbols to identify an alpha particle. And we'll be talking about alpha particle emissions in a minute. The most common ones, I would say, is the 4-2 helium symbol and the Greek symbol alpha, lowercase alpha. It is true there is a charge on this particular particle, 2 positive, and the reason why is there's 2 protons, 2 neutrons. That's what gives us a mass number of 4. But those 2 protons do not have 2 electrons. And so the overall charge of an alpha particle is 2 positive. All right, beta particles. Beta particles is when a neutron loses a beta particle, and that neutron becomes a proton. So the symbols for a beta particle, when we're using it in terms of a nuclear equation, this is the most common form used. When we just want to symbolize it very quick and easy, we use the, again, lowercase symbol for beta. Now, the difference between an alpha particle and a beta particle, alpha particles, because they have mass and they have size, they can be stopped by thin sheets of plastic or even paper, and so they're pretty easy to control and to contain. The downside of an alpha particle, a lot of times, sometimes labeled under the group of low-level radioactive waste, is they tend to do quite a bit of damage once they get inside of the body. They have mass, they have charge, and they can either ionize water, or which may cause disruptions or rearrangements of molecules within the body. Probably the one we're most concerned with is our DNA. Beta particles, on the other hand, they don't have much mass. They have 0 mass, or very little, very, very small amount of mass, and they have a -1 charge, so they're not as the magnitude is not as great as a 2 positive charge of the alpha particle. They do penetrate a little bit further than alpha particles, and so that's the concern, is the penetration of the alpha particle, maybe through the first few millimeters of skin. A positron is just the opposite. It's an opposite charge of an electron, and this is when a proton would lose a positron and become a neutron. So we have beta particles where the neutron loses a beta and becomes a proton, and then we have positron emissions where the proton loses a positron and becomes a neutron. And the reason why they stress this in this chapter is that In the medical field, we use positron emission tomography. So we use positron emission to help diagnose maybe cancers within the body. Oh, let's say one other thing here. Again, how do you know it's a positron? Well, it's a positive 1 here instead of a negative 1. And again, this could be written like E with a positive 1 and a 0 like that. All right, next is the gamma rays. Gamma rays have the most penetrating power. They're generally attenuated through concrete or lead. There's natural occurring gamma rays from the sun. Many of those are rerouted around the Earth because of our atmosphere. But gamma rays, as they pass through the body, they're highly energetic. They can do a lot of damage as they pass through the body and ionize multiple atoms and molecules within the body. So the thing about a gamma ray is you notice there's no mass number and there's no atomic number. It's just energy. So ionizing radiation is anything that produces a trail of ions as it goes throughout the material. All right. So as alpha, beta, or gamma radiation passes through the body, it can knock electrons off other substances. And again, the most penetrating is the gamma ray. It is just a ray. It has no mass, and it can pass completely through the body. Then beta, and then alpha, because it's got mass and size, it doesn't penetrate as much as beta or gamma. So we need to be able to write a nuclear equation that can symbolize the emission of an alpha, beta, or gamma radiation. So the main things to remember is that matter cannot be created or destroyed. So the mass on both sides of the nuclear reaction have to equal out, and the sum of the atomic numbers on each side must be identical. All right, so here we have uranium-238. So the things we want to focus on are the mass number and the atomic number. So here's uranium-238. It does an alpha decay. How do we know it's an alpha decay? Well, when we see this as a product, the 4,2 helium nucleus, then we know that's an alpha emission. And so if we take 238 minus 4, that would give us 234. And then if we take 92 minus 2, that would give us 90. So now the atomic number has changed from 92 to 90. We have to go to the periodic table and find out what chemical symbol represents atomic number 90, and that would be thorium. So off the periodic table, if you look at atomic number 90, it's thorium. So here is the first time we see that in chemistry there is the ability to change from one substance to another, from one element to another. And remember, that's what alchemy was all about. It was trying to change lead into gold. And chemically, that cannot be done. Chemically, we're only working with the outer shell electrons. But here, in this nuclear equation, we are actually changing uranium into thorium through an alpha particle emission, or an alpha decay. So that's what you're going to be expected to do in Chapter 9, is to be able to write equations based on alpha, beta, and gamma emissions. So beta, here we have nitrogen 16, and we're going to lose a beta particle. All right, so 16 minus 0 is still 16. 7 minus a negative 1. Remember, minus a negative is a positive, so 7 minus a negative 1 would make 8 here. So that's how we figure out what the mass number and atomic number are. 16 minus 0, still 16. 7 minus a negative 1 gives us 8. 16 over 8. So oxygen 16 is formed. The other thing you could do is you could have this as a blank and be asked to determine what that is. So you'd say 16 minus 16 is 0. So 16 minus 16 equals 0. And 7 minus 8 equals negative 1. So we'd have 0 as a mass number, negative 1 as the atomic number, and that is an indicator of a beta particle. All right, positron emission. Positron emission, again, you don't see a change in the mass number because the mass of the electron is negligible. When we see a decrease in the atomic number by 1, that tells us some particle was emitted that had an atomic number of 1. And the only thing we've talked about that has a positive 1 atomic number would be the positron. So this is probably the most common way it's written when we're writing an equation. I've gotten a little fancier here and put the beta with it, but again, because it's a positive 1 beta, it's a positron. Gamma is pretty easy to see. There's no change. We see that the mass number does not change, nor does the atomic number change. This is strictly energy coming from the nucleus. And you say, where does the energy come from? Well, think of the nucleus as vibrating, and it's vibrating. Something has caused it to vibrate violently, and through the release of the gamma, we see a lower energy state for the nucleus. So we're not losing protons or neutrons, and so therefore we don't see changes in the mass number or the atomic number. And again, remember, gamma rays, not particles, gamma rays have the most penetrating power. So here's what you're going to be expected to do. You should be able to predict what X will be in this reaction based on what you start with and what type of emission is happening. So tell me what type of emission this is. Well, we see the electron symbol, we see a negative 1 charge, so we know that this is a beta decay because we see a beta particle being emitted here. So again, we know 239 minus 0 is 239, so the mass number is not changing. And then 92 minus a negative 1, that's the same thing as adding 1, so we would get 93 for an answer here. So then we look on the periodic table and find out which element on the periodic table has an atomic number of 93, and that would be neptunium. So we know now that it's 93, we can look up the chemical symbol for it, and we know that the mass number did not change, so this is the symbol X that we solve for. So where does this nuclear energy come from? Where does this radioactivity come from? Well, there's a binding energy that holds the protons and neutrons together. Remember, protons don't want to be near each other. Like charges repel each other. So the neutrons can buffer some of that like repulsion. But there is an energy called the binding energy that holds the nucleus together, the protons and neutrons together. So when the nuclei decays, some of that energy is released and we end up with hopefully a more stable nucleus. So stable radioisotopes. So nuclear stability correlates with the ratio of neutrons to protons. For light atoms, it's about 1 is a typical stable. So 6 protons, 6 neutrons. Nuclei with larger number of electrons, 84, tend to be unstable. So when we get to about 84 polonium on the periodic table, that point on, we believe most of the nuclides are unstable, that they are going to fall apart or decay and release alpha, beta, or gamma emission. Then there's these magic numbers. We find that when there's an even number of protons and neutrons, they tend to be more stable. So you go, why is that so important? Well, when we're trying to discover new elements, maybe one that's not in the universe, we're looking for these islands of stability. Maybe we make a new material that is stronger than any other substance in the universe. So we look for things like that's why we take time and money and effort to try to make new elements to see what these new properties would be. Would they be properties that are different than what's in our universe today? So again, even number relatively stable, odd number generally not as stable. And all isotopes with more protons than neutrons are unstable, except for hydrogen 1. Remember, we know that's the general form of hydrogen, because if we look on the periodic table, the average mass of hydrogen is 1.008. So we know that the first isotope or nuclide of hydrogen is the most stable and the most prevalent in nature. All right, here's the next big major concept, and that's half-life. And that's the time required for 1/2 of a quantity of substance to undergo change. So for radioactivity, how long does it take for half the radioactivity to decrease for an atom? And that can range from fractions of a second to billions of years. And this is the concern with those who look at nuclear energy. It's what do we do with the waste from nuclear energy? If its half-life is billion years, then that means that the radioactivity does not decrease by half for a billion years. So that area becomes unusable. We consider it a dead zone, and we see things like that with Fukushima and Chernobyl. At the same time, other half-lives are very short. We have, a lot of times, the short half-lives, we have medical uses where we need a burst of energy, maybe to kill a cancer cell, but it maybe has a half-life of 1 second. So after 1 second, you're at 50%, 2 seconds, you're at 25%, 3 seconds, you're at 12% radioactivity, and so forth, or 12.5%. So that a lot of short half-lives have some medical application. Oh my gosh. All right, so here's some selected half-lives, and so we see carbon-14. This is what we use in radiocarbon dating, and based off of the half-life of carbon-14 and what was once a living substance, we can determine how many half-lives have passed and give us a predictor of how old the object is. The main thing with carbon-14, it had to be living at one point, and we'll talk about that a little more. Cobalt-60, 5.3 years. Hydrogen-3, 12.3 years. Where would you see hydrogen-3? If you have a watch that has glow-in-the-dark markers, and they glow for, they don't require you to shine light on them for them to glow. They just glow on continuously on their own. A lot of times tritium, hydrogen-3, is used as the energy source to keep those markers glowing. It's all contained within the watch. There's no radioactivity released by the watch. It's actually contained within the markers themselves. Iodine-131, that was a concern with Fukushima because they were afraid the iodine, a lot of times when there's nuclear reactor energy releases or radioactivity released, iodine-131 can be one of those. And so people would, on the West Coast, were taking iodine tablets to saturate their thyroid with iodine, so this radioactive iodine would not reach the thyroid. Iron 59, molybdenum 99, sodium 24, strontium, technetium. You see technetium, which is used in the lab for a positron emission tomography, 6 hours for a half-life. So with positron emission, you may be in the hospital for some time isolated just to get down to an acceptable exposure of radioactivity. And then look at uranium-235, 710 million years, just for the half-life. So you start off with 100% uranium. 710 million years later, you're at 50% radioactivity. So that's the major concern about uranium. So the decay is a first-order reaction. It's very quick at the beginning because you have a lot of atoms that are radioactive. As we go through these different half-lives, it starts to come to equilibrium. So we've seen this type of curve before when we talked about equilibrium. And so we see a decay very quickly at first because the concentration is high, and then it slowly tails off as we... and I guess I shouldn't say this is an equilibrium in that it is constantly decaying. It's just not decaying as fast. All right, so here's the type of problem you could expect to see. A patient receives 10 nanograms of radioisotope with a half-life of 12 hours. How much will remain in the body after 2 days, assuming radioactive decay is the only path for removal? So you're not excreting it. It's staying within the body. We want to know how long it takes. How much will remain after 2 days, all right? So here we know it's 10 nanograms per 12 hours, and 12 hours is a half a day. So if we take 2 days and divide it by a half, that will tell us half day, 12 hours, which is half a day. That tells us how many half-lives we have. So 2 divided by 0.5 is 4 half-lives, all right? So 4 half-lives. So we start with 10. One half-life would get us to 5. The second half-life would get us to 2.5. The third half-life would get us to 1.25. And then the last one would be 0.625. And they rounded this off to 2 significant figures, and we get 0.63 nanograms. All right? So this is a good... So here's 1 half-life, here's 2, here's 3, here's 4. And if you're taking my general college chemistry, there's an actual, we could actually use an equation that could determine this. But for chemistry 140, this is probably the easiest way is to actually just show it as step-by-step reductions of 50%. So in radiocarbon dating, there's a certain amount of carbon-14, which is a radioactive carbon in the atmosphere. And we have carbon-12 mostly in our bodies, and with a little bit of carbon-14 that we get from the atmosphere. And the ratio of carbon-14 to carbon-12 is stable for living, breathing plants and animals. So what happens, and the way this, well, before we... The way this carbon-14 is produced, there's nitrogen-14 in the atmosphere. It gains a neutron. Now, a neutron, look at this. This is the first time we've seen this. It has a mass number of 1, but it has 0 for the atomic number. So it increases the mass. And in this case, what it does is it causes the emission of a protium atom, and that makes carbon-14, which is a radioactive form of carbon. So, as long as we're living, that ratio stays constant, and that's the big assumption, that this has been constant throughout the history of the Earth. So once you die, once this substance, living substance, dies, so it can't uptake any more carbon-14. So the carbon-14 starts to decrease in the object, the once living object, back to nitrogen-14 through a beta decay. And so from how much carbon-14 has been emitted, and we know the half-life of carbon-14, which we talked about in a previous slide, over 5,000 years, we can determine how old the object is. So the half-life is 5,730 years. The carbon-12 doesn't decay, but the carbon-14 does. So that ratio allows us to predict once living things up to about 50,000 years old, or one half-life. Or 9 half-lives. Yeah, 9 half-lives, I should say. 9 half-lives. All right, last section that we're going to cover, energy production. We go back to Einstein's equation, E equals mc squared. E stands for energy, m stands for the mass, and c squared is the speed of light, which we've talked about previously in a chapter. And that would be 3.0 times 10 to the 8th meters per second. All right, and that's squared. So that's where we get the production of energy. So just a small little mass multiplied by 3.0 times 10 to the 8th meters per second. Square that term, and we get 9 times 10 to the 16th power. That's a huge amount of energy, even if you've got a very small amount of mass being converted. So that's small amount of mass lost in the nucleus as the atom splits, and the binding energy release, that releases radiation that we use for nuclear power. So the way we usually do that is we use this heat given off by this decay to heat up a fluid, which then converts water into steam. The steam runs the turbine, which generates electrical energy, and we use that for the electricity in our houses, if your house is powered by a nuclear reactor. So, in order for this reaction to happen, we have to split the uranium-235 atom. All right, we have to split the atom. So again, we got this massive nucleus, lots of protons and neutrons, 235 protons and neutrons in uranium-235, right? So we fire a neutron at the atom, or the nucleus. The nucleus then falls apart and makes uranium-236. And then from there it falls apart into krypton-92, barium-141. And it releases 3 more neutrons that could be used to split 3 more uranium-235 atoms. And the big thing that comes out of this is energy. So we can use that energy at the end of this equation to heat water so that it can generate steam, which can generate electricity. So it's self-perpetuating in that we added 1 neutron, we get 3 neutrons out, and those 3 neutrons can now go and hit some more uranium-235 nuclei and cause this happen again. So that's what we like about it. Little impulse in of neutrons, and then all of a sudden it starts taking off, and we call that propagating. And so what this looks like, we look on the next slide. Here's the neutron coming in. Here's uranium-235. Uranium-235 splits. Some of the binding energy that was holding this large nucleus together is converted to energy. And then 3 neutrons come out. If they happen to collide with 3 other uranium-235s, they split. And then there's 3 more neutrons released. And here they show these 3 neutrons hit 3 more uranium-235. Same thing here, but this one of them misses. and that's typical. And if we can control this chain reaction, we can generate how much energy is going to be released. So if we need more electricity, we open up the control rods, which we'll see on the next page, and that causes more heat and energy to be released, which allows more steam to be produced. Or if we pack this in really tightly, we can get a large amount of energy released at one time, and we get a nuclear weapon. So what I want to show you is that in the United States, our nuclear reactors must be in a concrete dome. This is so that if there is a nuclear disaster, it is to be contained within the dome. We just seal the dome off and everything would be contained within the dome. Some people argue whether that would actually happen or not, but that is the design of the structure. Here you have what we call the reactor core, and you have rods that contain uranium, and then you have control rods that you adjust in and out depending on how much energy you want released. Do you want the reaction to happen faster or slower in releasing energy? So that energy then heats up a fluid, and they show it as water here, and that water then is transferred into a secondary reactor, and you see the water here that's converted to steam. The steam runs the turbine, generates electricity, and then the reused water, we condense it. This is where you have the cooling tower, those conical structures that look like this. Actually, not conical, it'd be more like a hyperbola. And so what happens here is the cool air updrafts up the cooling tower as the water flows down, cools the water out, and we pump it back in here to use it again. And at the same time, we pump new river water out or lake water out and return some of the water back to the lake. So that's why you generally see power plants by rivers and lakes. So, if you look at Chernobyl, what happens is these rods are made out of carbon. That's what slows down this process of decay, or emission, I should say. And so this all fused together, and energy built up, and it actually blows the top off of the plant, or the nuclear, I want to say that, the plant. Fukushima, the pumps stop, backup generators fail because of the tsunami, again, overheats, and there you saw a big explosion coming out the tops. All right, the Holy Grail we're looking for is nuclear fusion. In nuclear fusion, we're going to join two nuclei together. And that's what the sun does. Through gravitational energy and heat, we can actually fuse the hydrogen nuclei together. That's the fuel for the sun. And large amounts of energy are released. We get a neutron release. That's not too bad. We don't see something that's going to be around for 700 million years for a half-life. And so the only problem is we can initiate this step, but it takes a lot of energy, and we're not getting that much energy out, and we can't, it's just not commercially productive. Lab in Livermore, California, they're trying to use large lasers to create fusion, and this is what we want, because here we don't have to worry about storing nuclear waste. So fusion is where we take two small nuclei and fuse them together to make a larger nuclei. And in that case, some energy, some of the mass is converted to energy, and that energy released, we could use that to, again, heat water to form steam. Breeder reactors, this has been talked about. This is sometimes controversial. I think Iran is what I'm thinking of here. Is that a fission reactor that manufactures its own fuel. So we can use a breeder reactor to actually make fuel that we could then use to make either rods for a nuclear reactor, or we could, the concern is this, a product here could also be made into plutonium-239, and then you could make nuclear weapons from that. So that's the concern with the breeder reactor. And the question is, do you need to manufacture your own fuel when, especially in a country that would have lots of oil reserves? So that's the concern. Is that what's really going on, or are they trying to make a fissionable material that could be used for a nuclear weapon? Instead of, typically what's done now is we mine uranium. Uranium's present in most of the ground, but there's richer deposits of it. We mine uranium, we purify it through these gas diffusion plants, and that's what you've been seeing in the news with the gas diffusion plants, trying to eliminate or minimize the number of gas diffusion cells, or I guess that would be a great way to call it. So with a breeder reactor, you don't need the gas diffusion. The gas diffusion takes a long time just to get a small amount of fissionable material. Breeder reactor, you can generate it fairly quickly. So that's the big concern there. All right. That concludes the materials on Chapter 9. What I want you to be able to do is to write isotopic symbols or nuclear symbols, be able to write nuclear equations with alpha, beta, and gamma decay, be able to talk about what the dangers of those particles are, or rays. Then we talked about half-life, being able to predict how much material will be left after a certain number of half-lives, or how many half-lives have to be gone through in order to get to a certain amount of material. And then understanding nuclear fission and nuclear fusion and the uses of that. Thank you.